Spiros.
Hello, Roger.
How you
Great
doing?
day today.
What's
I'm going great.
Good.
I'm going fantastic.
So we're going to talk about the EcoGlobal project and the hydroxy generators that you've been working on for well over a decade. Just tell us a little bit quickly about your background.
My background is mechanical engineering, and I linked up with a Professor Yul Brown many years ago, and he taught me physics, Russian physics, not Eastern physics. Russian physics is not black and white, it's grey. And that's why we have got the facility of the discovery of hydroxy gas, because it's a volatile gas, and of course nobody wants to go near it. But no, what did happen, once we developed it, he found that the gas imploded, was not, and it's in situ, it's safe to produce. So, and you took away the diaphragms. The two schools of thought are out there on the engineering side. Teledyne Brown, for example, and a lot of other companies, they are separating the hydrogen and oxygen for safety aspects, but that is not the case. If the gas implodes, then it's safe. If the gas is made in situ, it's safe. The only gas that's available is what's in the containers, in the lines. In other words, it's gas as required on the spot, in situ, from the sun, directly from the sun, DC power, to the generator, which marries with the generator perfectly, through a chopper, which is part of the reliability function that I developed at Macquarie University.
Okay.
Now this is
look,
the beginnings
we've
of
got a
it.
presentation here, Spiros. Let's take folks through the presentation to kind of put them into perspective.
Yeah, we'll go step by step.
So, okay, so essentially EcoGlobal is producing green hydrogen, as Spiros just said in the introduction here. There's the whole idea is that we can take renewable energy as an electrical input and run it through the so-called hydroxy generators, which takes water and it creates hydroxy gas, and we'll show you some examples of that. And essentially then you just separate that into hydrogen. So it's a lot more, we would say a lot more cost effective for many, many reasons. So
cost effective and cost efficient as well.
Right. So for instance, here we've got our claim here, so to say, lower maintenance, it's scalable, economic. It's also, we're going to demonstrate how we can use it for waste management and also for clean burning coal power stations. So, yeah, carry on.
Well, when you say clean burning coal-fired power station, what that means, in essence, is carbon neutral burning. No CO2 given off whatsoever. In other words, we're taking care of the problem is that you can burn coal, but don't burn it your way, burn it our way, which we're going to show you more information on that further down in the presentation.
Okay, so it is a publicly listed private company with over 150 investors. And there's a quick little intro. You've been involved with R&D around hydroxy gas for a couple of decades now, with a very, very interesting background, because you were the guy who really put everything together for Yul Brown, who was the so-called inventor of Brown's gas. He passed away a few decades ago, but you were the guy who was putting everything together in the workshop.
That's correct. He taught me the beginnings of it, and we finalised it with the university, and a bit of, so the big problem with the hydroxy generators when Brown put them together were not reliable. Now the hydride material, which again the slide you'll see it, is developing on the surface in a proprietary way in the patent applications, protecting it all. And it has, in essence, already signed off 10-year life, but the way I did it, it probably gives us 20-year life. The same efficiency, cost efficiency and reliability of photovoltaics. So the marriage between DC power photovoltaics and hydroxy generators is perfect. There's a perfect synergy.
Let's take folks through this process of education around this. For those who don't know it, you know, we're talking about a form of electrolysis. And so the usual process with electrolysis, it requires quite a bit of energy to split water into hydrogen and oxygen. And essentially that process hasn't changed, you know, since Faraday's day. And of course, you know, they have got a bit more sophisticated with electrolysis, but it still requires quite a bit of energy, and they have internal diaphragms and maintenance costs, etc. And so we're bypassing all of that by basically using what we call the hydroxy generators. So it's still water in and hydroxy gas out, and there's a DC electrical input. But your claim to fame here is that you've been producing these hydroxy generator prototypes using low-cost materials like mild steel. And just say a little bit about this process with the hydroxy generators that you've patented.
Well, I use mild steel because mild steel is worth $2,000 a ton. Now, I did make some out of nickel because everyone's making nickel electrodes. They last longer, of course they do. Those particular electrodes are worth $2 each, where the steel ones are 2 cents each. So there's a differential in cost efficiency. But what we did, we manufactured or compiled, or we worked out a way on how to make the steel electrodes as reliable as nickel, which we have. Mm-hmm. In fact, more reliable. Because what we're doing is producing hydrate. You can see the photograph on the right-hand side, the grey material on the surface of that plate. Well, that's hydrate material. And that goes off and on. In other words, it plated on, plated off, plated on. And we believe on the concentrations of hydrate, that could have 20-year life, that plate, and it's mild steel. Cheap to produce, cheap to manufacture. A cheap hydroxy generator means cheap hydrogen.
So
means we can make lots of hydrogen.
Essentially what you're saying here, it's the economics of scalability. To, like, if you're needing to manufacture 20,000 of these, right, for a green hydrogen plant, we can economically do it much, much, much cheaper than anybody else. Plus,
absolutely, absolutely,
idea that we've pretty much proven up that it's long lasting. Unlike conventional electrolysis, you know, it might last 7 to 8 years, and then they have to replace it, or you know, a lot of things. You're basically saying that this can last 15 to 20 years easily with all the innovation.
Well, I mean, what's happened is Macquarie University, when we did the first trials, they signed off on 10-year life. Yeah. Now, I mean, I increased the metallurgical properties of the place by changing the configuration of the electrolyte, and I believe they're going to go 20 years.
So, for instance,
maybe even more.
Slide up here, which gives us a summary so far. No expensive materials. This is mild steel, whereas competition has to use all sorts of exotic materials. Incredibly low maintenance, no obstruction, like there's no internal diaphragms, because we just simply do external separation, which is off the shelf.
That's right. External, and let me just say this, external separation is much more reliable than internal separation. Why? Because the hydrogen atom is so small, it'll go through and leave the oxygen atom behind. Membrane separation, and there's also catalytic separation, which we're working on, and we can do that externally much more efficiently than inside the cell technology, where they separate the hydrogen oxygen because they're scared, frightened of detonation, explosion of the actual device. But as we know, what Yul Brown discovered, actually, he discovered it, the gas implodes. 1 litre of water produces 1,860 litres of gas. When detonated, produces 1 litre of water and 1,859 litres of vacuum. That's another product, which is vacuum technology, right?
Okay, well, let's just keep going through it.
Which makes it safe. And on top of that, Roger, on top of that, the gas is made in situ. It's only what's in the lines. If you get a lightning strike, for example, and you've got 150,000 generators, what are you going to get? You're going to get a detonation? Yes, you will. Static electricity, but it will not explode. It'll implode.
Okay.
In the line.
You know that there's,
so all you'll have is you'll have downtime, but no danger to the public at all.
Yeah, good to know that there's good safety protocols around this. So we're talking about external separation, unlike the competition. And of course, you've innovated some very interesting other formula around giving it even longer shelf life. So
yes.
So here's a little slide here for most people will know about conventional electrolysis, which basically they're using now with the emerging, green hydrogen economy, where we've got some slides further down the track. It's an emerging multi-billion-dollar industry. People are desperate for making economic hydrogen. Now, for those who don't know it, hydrogen is made also from fossil fuels, steam reformation process. And that's not what we call green hydrogen. That's generally referred to as blue hydrogen. So, and that's still, it's dirty hydrogen. It's still made from fossil fuels. So when we use the term green hydrogen, it's completely made from renewable energy sources. Some of the prohibitive factors for this has been the conventional electrolysis. It's expensive to run. It's a lot of energy input, but that's what they're using at the moment. And we're offering a really, really good alternative to that in terms of scalability, maintenance, etc. So the Hydroxy, you have essentially patented this based on no expensive materials, low maintenance, scalable, and long shelf life, right?
Yes.
And here's just like a little diagram, energy in, hydroxy out, and water in, hydroxy out, and of course we can use any means of electrical input. It could still be grid electricity. Don't forget, if you just want to get hydrogen, made more economically than what it is, you can use the grid electricity. But ultimately, you could be using this with solar power plants and wind and any other, hydro, etc. So tell us a little bit about hydroxy gas, Spiros. It reaches
about hydroxy gas. Well, we get to come to that, but the high temperature effect of hydroxy gas is one of the main reasons we're going down this track of coal-fired power stations where we can destroy the CO2 molecule. Not just the wrong word, destroy is the wrong word. Change it to carbon and oxygen. And what you can do with that oxygen, you can sell it. What you can do with the carbon, you can sell it. And if you want to keep some CO2 behind, don't just destroy all the CO2, you can make methanol. So you can have a coal-fired power station making methanol.
Okay, well, we've got some slides there later on, Spiros, about the coal power. But just for the sake of people, they've never heard of hydroxy. Essentially, we're just changing water into its components of separating hydrogen and oxygen. And it's a mixture of those two molecules, and that's what's referred to as hydroxy. And as you can see, it's got some special properties. Hasn't really been researched much. There's still not even one PhD paper written on this, and it's got these remarkable qualities to it.
Well, that's correct, because the scientific community will not recognize implosion. And I've got an implosion device in my factory happening every day. Now,
up on
this is one of the
website, Eco Global Fuels, up on the homepage, you will be able to watch a demonstration of hydroxy being made and also the whole implosion process. You'll see it there.
Yes, that's good.
A filmed whole, for those who want to research this, there's like about an hour of demonstrations there. And so there's been quite a few validations. One particular was in Macquarie University. Basically, they had the hydroxy generator that Spiros has created, and they ran it for hundreds of hours, and they documented the energy in, how much hydroxy was out, and the wear and tear on the tubes. So that's all been very, very well documented. And since that time, Spiros has actually innovated a lot more. So the design is even more efficient than this validation report, which was very,
we reduced the size, we reduced the weight of it, we reduced the size of it, and we increased the reliability of it. We've done that. Over and above what we did at Macquarie University.
Through, as you can see from this.
And we've got two PCTs going to, which is world patents. One's on the cell technology, one's on the tungsten reaction tube, and another one's going to be a process patent on how a coal-fired power station can operate and deliver power, green power, with no CO2 emissions, and none whatsoever, zero.
Yeah. So
that we can given we get the money that we can build now.
So we'll listen to this little video that we've put together.
Brown's gas, better known as hydroxy gas, is one of nature's.
Is that loud enough, Roger?
Yeah.
Following a history that dates back to 1800, William Nicholson discovering electrolysis, Michael Faraday developing the theoretical laws of electrolysis, leading Ewell Brown to an amazing discovery. Separating water into its components, hydrogen and oxygen, producing the gases together, and then burning the gases, produced energy. When burnt, the byproduct is water again. Developing a reliable and scalable means of producing hydroxy gas has taken Spiros 28 years of painstaking research and development. The ingenious system uses simple mild steel anodes and cathodes suspended inside a tube containing electrolyte. Each tube, or hydroxy generator, contains around 10 litres of electrolyte and can produce up to 18,000 litres of hydroxy gas. This can be scaled up for commercial applications. In an attempt to commercialise the process, Spiros and his team added hydroxy gas to a process of waste reduction used for the destruction of old car tyres. The results were astonishing. A combination of waste hydrocarbon gases from the pyrolysis of tyres or waste product, mixed with hydroxy gas and combusted, neutralised the toxic hydrocarbons in open air. In this demonstration, only toxic hydrocarbon gases are being burned. As we introduce hydroxy gas, the toxic hydrocarbons begin to be neutralised and form an envelope inside the blue flame. The combination of toxic waste gases and hydroxy gas burn in the open air at about 600 degrees Celsius. An additional and revolutionary discovery was made by Spiros through a series of experiments. When these combusting gases are introduced into a sealed reactor tube, the gases continue to combust, resulting in an exothermic reaction without the need for air. Airless combustion was discovered. In the reactor tube, the combined gases burn at a temperature in excess of 2,500 degrees Celsius. The exhaust flue gases contain syngases. These gases are captured rather than being released into the atmosphere. The system, therefore, requires no chimney stacks. Syngases, when compressed in a catalyst, produce methanol that's used commercially to produce plastics, paints, and a multitude of other commercial products, removing carbon and toxins from the environment, locking carbon away in everyday products. Energy produced from the exothermic reaction in the reactor tube can also be captured to generate power, so the system can be completely self-sustaining. The whole system is inherently safe because of the very nature of hydroxy gas. 1 litre of water produces 1,800 litres of hydroxy gas, When detonated, hydroxy expands and contracts at 0.06 of a second, which results in a net implosion, meaning there is no expansion and therefore no destructive capability, which makes it suitable for large-scale commercial application. Let's see the process of net implosion. Water is held in this reservoir for the purpose of this demonstration. As hydroxy is introduced, the water is pushed into the perspex reservoir. The bubbling is proof that the first reservoir is full of hydroxy gas. The pressure in the first reservoir is at 1 atmosphere or 0 pressure. Let's detonate the gas. If the gas exploded, it will displace the water in the perspex tube, forcing the water out. What has in fact happened is the level has actually fallen, proving that the hydroxy gas has imploded. The same occurs when the gas is under pressure. The system developed by Spiros has far-reaching implications for the safe and commercially viable destruction of waste product. The production of methanol at 3 times less carbon footprint than conventional methods of production, producing carbon black used as an industrial colouring agent, the recovery of steel, with strong interest from CSIRO, Melbourne University, University of Queensland and Macquarie University to conduct third-party assessments of all aspects of the process. EcoGlobal Tyre Resource seek the support of government and the private sector to commercialise this technology in the waste disposal sector, initially with the recycling of tyre product and potentially other waste streams. Our science is pollution-free and protects the environment for generations to come.
Good. Okay, so very good. So here's a slide with the off-the-shelf separation technology. So far we've got these hydroxy generators that are scalable, economical, robust, long-lasting. They take the DC and water and change it into hydroxy gas, and then it's just a matter of using off-the-shelf technology to separate the hydrogen and the oxygen, both commodities. So this is just an example of the off-the-shelf technology for separating the gases. Now, the infrastructure around hydrogen is developing very, very fast. So up on EcoGlobal Fuels, up under news, you can see a lot of multi-billion-dollar investments and infrastructure projects globally happening. In Australia, they're building, wanting to get in on the game, and pretty much all over the show, like in Europe and Scotland and Germany, and of course USA. A lot of hydrogen projects happening, right? Now, some of them are green and some of them are blue hydrogen. A lot of them are very blue hydrogen because it's cheaper at the moment to make blue hydrogen for obvious reasons. It's from fossil fuels. Green hydrogen is the ultimate goal, and it's the only thing that's holding back is the cost efficiency of that. And we're saying that the EcoGlobal Fuels approach is the missing link for that. So yeah, so there's a lot happening in Australia. One of Australia's most wealthiest individuals, Andrew Forrest, basically he's he's making steel and he ships out iron ore to the world, and he's becoming obsessed about really wanting to produce hydrogen, green hydrogen for Australia, and then turn his whole operation, steel making, into so-called green steel. So remember, once you've got hydrogen, there's a number of things you can do with it. You can use hydrogen as a storage for solar power plants. You can use it like a battery. And of course, you need hydrogen to make ammonia. And ammonia, of course, is another way of shipping hydrogen from, for instance, Australia to Southeast Asia. They're already starting to do that, right? So it's not just for agricultural purposes, but you use ammonia like a battery, and they can just separate it at the other end. So there's a lot going on here. None of these guys know about our project here. We need a lot more exposure. They need to hear about this. Now, of course, you can look up why we need hydrogen. There's a lot of good information on the website now. Power, of course, fuel cells for cars and small.
Yes.
Spiros is
I just want to say,
scalable at any level. It can be used also for like a hydrogen refueling stations. But of course, it
can I say something here, Roger?
Hydrogen heating. Spiros, you have something to add?
Yes, I do. The fallacy right now is, and New South Wales University agrees with me, they have developed a hydrogen battery. If they store the hydrogen to power fuel cell to power a car, right? Or power a household. Now, hydrogen in a titanium hydride solution is totally safe. The fallacy is this, and the comedy that came out of it, a big chuckle with the professor which I was talking to at New South Wales University, I don't want to mention his name, but is that you compress hydrogen at 10,000 psi, you're looking for trouble. Why? You don't have to. Titanium hydride absorbs it and it seals it in a container and it's non-flammable. And you release it by adding 100 degrees Celsius and you use that hydrogen anytime you want. Perfectly safe way of storing hydrogen. We are working towards that direction. Just imagine, right? You're on a farm out in the outback. You're about 50 miles away from the service station. So you have photovoltaics on your roof. You can run your tractor, you can run your harvester, you can run your car, you can run your house, all from hydrogen from the sun. Totally carbon neutral. That way, hydrogen, when you look at the internet, it is as powerful as diesel. When you take away the losses of a fuel cell, which is 50%, the other 50% comes from the hydrogen, means it's exactly the same power structure as diesel. So therefore, hydrogen is better, safer, more pollution-free. That is the hydrogen economy. I dread to think that those fuel cell cars in Japan, if one of them blows up, we're back to square one. Because they'll say, oh, it doesn't work.
Nothing like that.
No.
Nothing like that's happened.
Not yet, but it's an accident waiting to happen. No, we can't go that way.
Hydrogen, as you know, just disappears very, very quickly up in the air when those sort of accidents.
10,000 psi hydrogen, Roger, is an accident waiting to happen.
Yeah. Okay, let's move on, Spiros.
I spoke to my engineer. I spoke to my engineers that will not have 10,000 psi in their engineering shop. No chance.
So
that's going to change.
We're short on time, Spiros. Let's just stick to what we got here. So you can tell us a little bit about how hydrogen can be used now for waste management. Yeah, so just give us an overview of that.
Well, the temperature. See, we have the temperature where they haven't. We can take the temperature right up to 3,000 degrees and it's totally remove all the toxins, destroy them all, and destroy so the CO2 coming off the waste management criteria, which is tires, rubbish, you name it, right? The same thing with coal, same thing with cement, same thing. Because everyone's using coal to make cement, we can take that CO2 from the cement given off, which cement gives off CO2, and what it does, we neutralize that CO2. 6% of all our CO2 emissions from the planet, on this planet, is coming from production of cement, and we need to make cement for the buildings. That's it. So we can do that as well. There's a lot of products going to come from this.
Okay, Spiros, can we just backtrack a little bit? Can you just give us an overview of how you can use this for waste management? We've got two more subjects to carry: waste management, and separate from that, so-called cleaning up the coal industry and how we can use it for carbon sequestering. So tell us about the waste management.
Well, the tungsten reaction tubes are going to do that. The temperatures involved will totally polarize the actual waste, and all the gases given off will go through the hydroxy gas and be neutralized totally, 100%. We've got reports. You can show the report. We've got a report here. That we took 17.2% CO2 and brought it down to 1% on one tube. We've got we've actually got 12 years. We've got progressive reduction of CO2. And what does it become? It becomes carbon, a commodity, and oxygen, a commodity. That's how you do it. High temperature.
Here's the report here.
There's the report. You can see down the bottom there, 70.
Folks that are getting their head around this,
Roger.
basically hydroxy reaches a very, very high temperature, and plus it's got, you know, we're talking like up to 3,000 degrees, and it's got unique properties like implosion. So basically you can be putting into these chambers, which we have actually designed and we're patenting, etc. You can actually pulverize this into its elemental components. And we've actually done some testing on this. This is an independent test from a local council here in Sydney, Australia, where basically—
and by another approved lab. That ALS is another approved lab. And they paid for the report. Lane Cove Council paid for the report. They were involved in it. We had nothing to do with it. We just supplied the gas. They took the sample to the lab and they had it analysed, and they paid for it.
So as you know,
they're waiting for us to develop the system so they can do waste management.
So yes, waste management is a huge problem, as you know, in the world. And now, second to this, we've actually got this whole system where we can clean up the coal. Coal is, as you know, at this moment, we still haven't made the total transition to 100% renewables. It seems to be still decades down the track, and there's still coal power stations being built all around the world. Yeah. So the fact of the matter is, if you can take that coal out, hold on, let me finish, Spiros. Just let me finish. I'll give an introduction, and then you come in. If two people talking at once is not good for those listening.
Okay,
so let me give an overview first. So basically, we're saying if you can keep the carbon on the ground, then coal is just like a commodity, like you're digging up iron ore and diamonds, and nickel. If you can keep that carbon on the ground, then it's a feasible energy supply to consider. So we've got a whole sort of process here that we've actually patented the process, but just give us an overview, Spiros, of your whole approach to the coal industry.
Well, see, the coal industry is entrenched within the Australian economy for starters. Without coal, all our superannuation is entrenched in it as well. They will not stop burning coal. Why? It is a compact baseload energy source. What the problem is the CO2. If you can burn coal with no CO2, you can burn coal. You burn it our way, not their way. That way, there's no CO2, there's no problem. The CO2 becomes carbon, you can sell it, oxygen, you can sell it, and leave some CO2 left behind to make methanol as well in a coal-fired power station. What we're going to do is retrofit our technology on an existing coal-fired power station so they can do all of that. The payback period on this is 5 years, not 25 years, because they've got 6 commodities, not one. They've got green power as well. Everything's green because what happens? If the coal is burnt with no CO2 emissions, it's green coal. For the first time in history, we can make green coal. They're not going to stop burning coal. They found deposits under the Nullarbor of 2,000 years of coal. You reckon they're going to stop burning it? Right now, China is buying our coal at $2,000, $100 a tonne because they need to power their infrastructure and their works over there. So the price of coal is double, but it doesn't affect us. It's good for the Australian market, but still is not very good for the atmosphere. We've got to change all that. Somehow we're going to get to China, and we're going to 46% of all the coal burners are in China. But I've got shareholders, and you're all welcome to join the shareholders if you want and help us launch this product to protect those shareholders from China and any other person who wants to reverse engineer or pinch the technology from the existing people to put the money in to launch this technology. And I really great And I'm really grateful they've done that, because what it means is that the future generations that are coming will have somewhere to live. I mean, the way they're going now, they're blind. They can't see where they're going. The few that can, but really our technology is there, but they can't see it because there's so many powers that be. I mean, the amount of money they make from coal, oil and gas is $600 trillion a year. How are you going to stop that? You have to bend with it. You can't stop it. You have to make it carbon neutral. I'm not going to stop burning coal, but we're going to make it carbon neutral coal, green coal. Then you can, then you'll be like the willow tree. You bend with the wind. You do not break. And you make your money for your shareholders. And everybody in the atmosphere, in the biosphere, and Mother Nature is happy. That's what we've got to do. That's what we have to do in the next 10 years.
Yeah, well said. I've got a summary up here. Storage, the new hydrogen economy, the hydrogen fuel cells, transportation systems, steel making, carbon neutral power stations. Of course, hydrogen is used a lot in chemical production and fertilizers, the green ammonia, and mining and ore separation. And to it, there's also the implosion effect, vacuum technology, and we've got oxygen as a byproduct. So as you can see, folks, that if you get the better cost efficiency happening with green hydrogen, it can really lend itself to a lot of energy inputs across the board. So cleaner and greener, we can reduce carbon, and we basically reduce garbage, efficient waste to energy process that we've got, and getting into the the cleaner green environmental energies. Is there some overall comments that you want to make before we sign off here, Spiros?
Yes, I'd like everybody to join in and help us. There's room for everybody. Anyone who's got talent, anyone who wants to be like a subscriber, anyone who wants to be involved, they can help us launch the hydrogen era. This is the beginning of the hydrogen era in storage, in efficiency, in safety, in reliability. This is what we have got to do, and this is what I'm doing right now. We're so close. We're an unlisted public company. We're going to be a listed public company, and it's going to be worth a lot of money, and it's going to be totally carbon neutral technologies, and launch the hydrogen era properly. Not half measure, not green, not blue, pink, or whatever. Green hydrogen is the way to go. The sun's energy, fortunately now, is not taxed. They don't put a tax on the sun's energy. So therefore you can use the sun's energy to make hydrogen, and you can store the hydrogen using the titanium hydride. We can store it, we can use it in cars safely at low pressure, not at high pressure. For cars and every other instrumentation where you're using hydrogen as a fuel source, all right?
Good. If anybody's interested, there's ecoglobalfuels.com. And of course, you can email me, ecoglobalfuels@gmail.com. I have been an early seed investor in this technology about over 10 years ago, and helped with the validation process at Macquarie University and all sorts of things. So it's a very exciting project. And as Spiros says, we'd love to have you involved. So any inquiries, of course, just send them through and we'll get back to you. So thanks again, Spiros. Thanks for that. And I'll be seeing you soon.
Thank you very much, Roger. Thanks for your help.
Ciao.